In this video, we are going to solve problem 5.10 that is taken from chapter number 5, Analysis and Design of Beam, and book name is Mechanics of Material by Beer Johnston, 6th edition. So statement is draw the shear and bending moment diagram for the beam and loading shown and determine the maximum absolute value of shear and bending moment. So you can see this is a cantilever beam having fixed support at point B, and from A to C there is a distributed load of 2 kips per feet and point load of 15 kips at point D. The total length of this beam is 12 feet. So you have to draw the shear and bending moment diagram, and then you have to determine the absolute value of maximum shear and maximum bending moment. So let's start with the solution. We will solve this problem by using two methods. First one will be the direct method. So I will write it method 1, which is very easy, clear, and after that we will solve it by using second method, that is first we will find the shear force and bending moment equation. Okay, starting from method 1, if you remove this fixed support at point A, so that will offer a reaction force which will be represented as By, as well as there is a horizontal reaction force which is Bx, and there is a moment which will be like this, reaction moment which will be Mb. So we'll find this Mb, Bx and By by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force toward right is taken as positive. So you can see only Bx which is acting horizontally and there is no other force, and this is in negative direction, so it means that minus Bx is equal to 0, and from this we get that horizontal reaction force Bx is equal to 0. Now we'll find the second reaction force by using another equation of equilibrium, that is sum of all movements about point B is equal to 0 and taking the counterclockwise movement as positive. And we know that from A to C there is a distributed load, and this distributed load when converted into point load, so it will be 2 times the length over which it acts. So 2 multiplied by 4, and that will be equal to 8 kip. Okay, and that will act at a distance of 2 feet from both sides, either from C or from A till the mid. Okay, so this is 2 feet and this is 2 feet. Now we'll apply this equation. So first force that will produce moment about point B is this 15, and perpendicular distance is 4 feet, and it is producing counterclockwise movement, so it will be positive. So I can write it 15 multiplied by 4, that is positive. The second moment is produced due to this 8 kips load, and perpendicular distance is now 10 feet, and it is also producing counterclockwise movement, so it will be positive. So I can write it plus 8 multiplied by 10. And the third moment which is producing which is the reaction moment Mb, that is clockwise, so it will be negative. So minus Mb is equal to 0. So from here we will get Mb will be equal to 60, 15 multiplied by 4 is 60 plus 80, clear, and that will give you 140, and unit will be kips into feet. So we get this reaction moment Mb is equal to 140 kips multiplied by feet. The last thing which we will find is By, and that we can find it by using third equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see 8 kip is downward, so 15 is also downward, so minus 8 minus 15 plus By is equal to 0. So I can write it plus By minus 8 minus 15 is equal to 0, and from this we can get that By will be equal to minus 20 plus 23, because By minus 23 will be equal to 0 and By will be equal to 23, and unit will be kip. Now we have all this reaction force, so we will find the shear force and bending moment diagram. For that I have to draw the vertical line from the end of this beam, just like here I will draw, clear. The first thing that we will find the shear force diagram, so again for that I have to draw horizontal line and to show length in feet. Okay, on y-axis you have shear force having unit kips, clear. Let's take one division is equal to 5. So 5 kips, so it will be minus 5, minus 10, minus 15, minus 20, and minus 25. Okay, starting from the very first point at point A, you can see shear force is equal to 0 because there is a distributed load. So for x is equal to 0, so 2 multiplied by 0, it will be 0 at this point. So first point will be this one, clear. Now we are going to find out the shear stress at point C. This is point C and this is your point D. Okay, and this is your point B. So at point C, it means that at x is equal to 4 feet. 4 feet. This load will be equal to 2 multiplied by 4, which is 8, and that will be minus 8 because the load is downward. So at x is equal to C, or at C we have minus 8. So let minus 8 is here. You can write it minus 8 kip. Okay. Now you can see that the distributed load is a horizontal line with 0 degree, and that is downward negative. So then shear force will be 1 degree higher, it will be a straight line, but slope will be decreasing. So it will be like this. Now moving from C to D, there is no load, so this shear force will remain same till point D. But at point D, you can see you have minus 15 load. So minus 15 and minus 8 will give you minus 23 kips. So shear force will change from minus 8 to minus 23. So let's say minus 23 is somewhere here. This is your minus 23. Okay. So shear force will change from this to this. And again, moving from D to B, there is no other shear force. So it will remain same horizontal. And at the end, you can see you have By, which is plus 23. So minus 23 plus 23 will give you 0. So this is your shear force diagram. Clear? And we will now move toward bending moment diagram. So for bending moment diagram, again, what I have to do is that I have to draw a horizontal line to show x in feet. And on y-axis, you have movement that will be kips into feet. Okay. Let me take one division is equal to 25. So 25, it will be minus 50, minus 75, minus 100, minus 150. Okay. Or 125, sorry. 125 and minus 150. You can take as per your own requirement as well. Okay. Now, what we will do is that you can see that area as area under shear force diagram gives you bending moment. So we will do that. We will take the first area under the shear force diagram is this one, from A to C, from C to D is like this, and from D to B the area under the shear force diagram is this. So we will split them into three areas. This will be your first area A1, which will be this one. The second area will be A2, and third area will be this one. So first we will calculate A1. So A1 is how much? You can see this is a right angle triangle. So its area will be 1 over 2. Its base is 4 feet and height is minus 8. So I can write it as 1 over 2 minus 8 times 4. And when you calculate it, it will be minus 16. Okay. This is area for region A to C. This is your point A. Okay. Now we will find A2, and A2 will be equal to how much? You can see this is a rectangle. So this will be, height is minus 8 and width is 4 feet. So minus 8 multiplied by 4 is equal to minus 32. And this is for region C to D. The third thing we will find is A3. So A3 is again rectangle. So you can see this height is minus 23 and width is 4. So minus 23 multiplied by 4 will give you how much? We have a calculator. 23 multiplied by 4 is 92, minus 92. And this is for region D to B. Now you have all these areas. So let's start plotting all these points. So at point A, we have movement is equal to 0 because x is equal to 0. Now this area, this is your point C, this is your point D. So area under the AC region is A1, which is minus 16. So first we will plot minus 16. So let's say minus 16 lies somewhere here. Clear? So you can see that shear force is a 1 degree line, straight line, and slope is decreasing. So bending moment will be a curve and it will be like this, clockwise direction. Now the second area, this is minus 16, this at this point. Now from region C to D, the area is minus 32, but at point D, we will have the total bending moment will be equal to A1 plus A2, and that is equal to minus 16 and minus 32, which is equal to minus 48. So we will plot minus 48. So let's say minus 48 is this point. Again, you can see that you have a shear force is a 0 degree line with a negative area. So bending moment will be a straight line, but the slope will be decreasing. So we will join these 2 points using straight line. And the last area is A3, which is how much? Minus 92. So at point B, the total area will be equal to A1. Our total bending moment will be A1 plus A2 plus A3. So A1 plus A2 is minus 48 and A3 is minus 92. So that will give you 140, minus 140. So at the end, we will have minus 140. So let's say minus 140 lies somewhere here. Okay. You can see that shear force is a horizontal line with 0 degree. So bending moment will be 1 degree higher. It will be a straight line, but slope will be decreasing. So we will get this point. And at the end, you can see you have this moment MB, which is how much? MB is plus 140. So it will bring back it to point 0. So this will be your BMD, bending moment diagram. So we have drawn the shear force and bending moment diagram. Now we will determine the maximum shear force and maximum bending moment. So for the second part, in part A, we have to determine the absolute value of maximum shear force. So you can see here the maximum shear force is 23. Clear? So I can write V max absolute value is equal to minus 23, and that will be equal to 23 kip. And for B part, we have to find the maximum absolute value of bending moment, and from this diagram you can see the maximum absolute bending value is 140. So I can write it maximum absolute value is minus 140 mod, and that will give you minus 140 kips into feet, and which is the answer of our second part. Now we will solve the same question by using another method that will be using shear force equation and bending moment equation. So in method 2, I will write method 2, and the method is by using shear force equation and bending moment equation. Once we get the shear force equation and bending moment equation, then we will draw the shear force and bending moment diagram. So what will be the first step? You can see you have three regions from A to C, from C to D, and from D to B. So we will take the region, first we will take region A to C. Now A to C means that X is greater than 0 and less than 4 feet. So this is the region A to C. Okay, so what we will do is that we will cut this beam at a distance of X, where X greater than 0 and less than 4 feet, and we will draw the shear free body diagram. So it will be like this. This is your point A. This is the distance where you have cut the beam. This distance is represented as X. Clear? And there is a distributed load over a length of this X, and the magnitude of this distributed load is given by 2 kips per feet. Okay, so when you cut it at this point, so you will be having a shear force which is acting downward V, and you will be having a moment M. And let me call this point as point J. So we'll find this M and V by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along Y direction must be equal to 0, and upward force is taken as positive. Okay, you can see you have a distributed load. So when this distributed load is converted into a point load, so it will be equal to 2 multiplied by the length over which it acts. So length is X, and it will act at a distance of X by 2 from both sides, from either side. So this distance is X by 2. This is also X by 2. Now we will apply this equation. So you can see the sum of all forces along Y direction must be equal to 0. So 2x, which is acting downward, so minus 2x minus V is equal to 0. So it means that V is equal to minus 2x, and unit will be kip. Now when you put the value of X for different X value that is defined over here, X is greater than 0 and less than 4 feet, you will get the value of shear force for the region AC. Again, the moment M can be obtained by using sum of all moment about point J is equal to 0 and taking the counterclockwise moment as positive. So about point J, the first moment is due to this 2x, and perpendicular distance is X by 2, and it is producing counterclockwise moment, so it will be positive. And the second is reaction moment, which is also counterclockwise, so that is also positive. So we can write plus M plus 2x into X by 2 is equal to 0, and from here we will get this moment will be equal to X minus X square, and the unit will be kips into feet. Now this is the moment for the region AC. Now at X is equal to 0, put it in this shear force equation. So you will get VA is equal to 0. And if you put it in this moment equation, so moment MA will be also equal to 0. So this is the value of shear force and bending moment at point A. At X is equal to 4 feet. So what we will get if you put the value of X in this equation, so minus 2 into 4 is minus 8. So we will be equal to minus 8 kip. And M will be equal to minus 4 square, which is equal to minus 16 kips into feet. These are at C, at point C, because X is equal to 4 feet at C. So V is equal to C and M is equal to C. Okay, now for the region CD and for region CD and just at D minus. Now what D minus shows that D minus shows that D, it is slightly before this point. Clear? Exactly. We can take this distance as 8, but we will not include this 15 kips load. And what we will do is that we will draw the free body diagram. So free body diagram will be like this. This is the beam from A to C. There is a distributed load of 2 kips per feet. Clear? And from C to D, this is C and this is D. So total distance is 8 feet. Clear? 8 feet. So what we will do is that we will convert this distributed load into a point load. So it will be 2 multiplied by the length over which it acts, and that length is, this length is 4 feet. Here this is 4 feet. So it will be 2 into 4 is minus 8 here, and that will act at a distance of 2 from both sides. So this will be 2 feet, and this will be also, the remaining will be also 2 feet. So when you cut it at D minus, so you will be having a shear force which is acting downward V, and you will be having a moment M as well. And at this point is point O. So we'll find this V and M by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So minus 8, which is acting downward, minus V is equal to 0. So minus V minus 8 is equal to 0. So from here we will get V is equal to minus 8 kip. Okay. For this moment, we will find the sum of all moment about point O is equal to 0, and taking the counterclockwise moment positive. So first moment is this moment which is counterclockwise. The second one is this 8 into perpendicular distance will be now. This total is 8. So 2, this is 2. So this will be 6. So this will be counterclockwise. So it will be also positive. So I can write it plus M plus 8 multiplied by 8 multiplied by 6 is equal to, not 8, 8 multiplied by 6 is equal to 0. So what we will get is that moment will be equal to minus 48, and unit will be kips into feet. This is just at D negative. Okay. Now for region DB, I will write here by using another color for region DB, and at B negative. Now B negative means somewhere here. So what you will do is that you will cut the beam and you will draw the free body diagram. It will be like this. This is your point A. From A to C you have distributed load. Again the same thing. And this is your point D, where you have a point load of 15 kips. Clear? And at point D, when you cut it, you will be having a shear force V, and you will have a bending moment B. The total length of this beam is now 12 feet till point B. This is 12 feet. This distance is 4 feet. This is 4 feet. And this distance is also 4 feet. Okay. So how we'll find? So first thing is that we will convert this distributed load, which is 2 kips. So 2 multiplied by length 4, that will be equal to 8. Clear? And then we will apply the shear force. Then we can find this shear force and moment M by using equation of equilibrium. So first equation of equilibrium is that sum of all forces in long y direction must be equal to 0. So again you can see 8, which is downward. So minus 8, this minus 15 because it is downward, minus V is equal to 0. So it means that V is equal to minus 23 kips. And this is just at B negative point, or you can also say that VB. Now we'll find this moment M by using an equation that sum of all moment about point B is equal to 0, and taking the counterclockwise moment as positive. So about point B, one moment is this, which is M, that is counterclockwise. So M, the second moment is due to this 15 kips load, and perpendicular distance is 15 into 4. This is also positive. So I can write plus 15 multiplied by 4. And the last one is that this 8 into perpendicular distance is now, this is 2, 4 and 4 is 10. So plus 8 into 10 is equal to 0. Okay. Now this M plus this is 60 plus this is 80 is equal to 0. So it means that moment is equal to minus 140 kips into feet. Okay. Now we have all these values. So what we will do is that we will just plot them. Clear? And we will draw the shear force and bending moment diagram. For that I will take this figure and I will copy it downward. Okay, like this. I will make it smaller. Okay. Now for shear force and bending moment diagram, what you have to do is that you have to take vertical lines from the end of this beam. Clear? And first we will draw the shear force. So again horizontal line and X in feet. Here on y-axis you have V shear force, which is in kips. Okay. Let one unit is taken as 5. Clear? Or you can also take it as okay 5. 5, minus 5, minus 10, minus 15, minus 20, minus 25. Okay, starting from point A, you can see you have shear force V is equal to 0. So your shear force is 0 at this point, clear? And at point C, this is your point C, this is your point D. If you project them, like this is your point C and this is your point D. Okay, at point C, you can see at C, V is equal to minus 8. So what we will do is that we will take minus 8 somewhere here. Okay, and you can see now the shear for the distributed load is a horizontal line with 0 degree and negative. So shear force will be a 1 degree line and its slope will be decreasing. Now, what is the moment shear force at point D? So at point D, you can see that at point D, you have shear force is again this one. V is equal to minus 8. This is for region CD or just before minus D. So V is equal to minus 8. And again, you can see from the first method, from C to D, there is no shear force. So it will remain horizontal till point D. Now, at point D, we have minus 15 kilonewton load. So minus 8 minus 15 will be minus 23. So it will be like here, somewhere here, minus 23. And at point just B negative, which is minus 23. So just B negative, it is minus 23. And at the end, you can see that you have this BY, which was plus 23, which will make it close. And this will be your shear force diagram. Okay. Now we'll draw the bending moment diagram. So for bending moment diagram, you have X in feet, and on Y-axis you have moment, which will be kips into feet. Let what we have taken in this, we have, okay. So what we will do is that due to limitation of space, we will take it minus 50, minus 100, minus 150, and minus 200. Okay. Starting from the first point at X is equal to 0, we have MA is equal to 0. So your first point will be this one. This is 0. At X is equal to C, we have moment is minus 16. So C is this point. So minus 16 will be somewhere here. Let this is minus 16. Now you can see that shear force is a 1 degree line and slope is decreasing. So bending moment will be a second degree curve and it will be like this. Okay, it will be like this. Now, what is the value of moment at point D? So this is, you can see this is the value, which is minus 48 kips. So minus 48 kips will be somewhere approximately here. Okay, now you can see shear force is a horizontal line with 0 degree. So bending moment will be a straight line using joining these 2 points. And the last one is moment at point B, which is minus 140. So minus 140 will be somewhere here. And again, shear force is a horizontal line with 0 degree. And this is negative area there. So what we will get is that we will get a straight line by joining these 2 points with slope decreasing. And at the end, when you will find the reaction force, which we have find over here, you have checked that MB was how much? This is plus 140. So minus 140 plus 140 will bring it to 0. And this will be your BMD, bending moment diagram. So from this SFD, shear force diagram and bending moment diagram, you can calculate the maximum absolute value of shear force and maximum absolute value of bending moment. So this, you can see this is minus 23, that is equal to 23 kips, and moment is equal to minus 140 mod, and that will be 140 kips into feet. So this was all about this problem 5.10 that we have solved by using 2 methods. And I hope you have enjoyed both the methods. And if you have any question, you can ask me in comment section. Those who are new to my channel, then subscribe it. And don't forget to hit the bell icon so that you can get notification about my latest videos. For any query, again, you can write me in comment section. Thank you for watching. Back in this video, we are going to solve problem 5.26 that is taken from Mechanics of Material, Beer and Johnston, 6th edition. So statement is, knowing that W is 12 kilonewton, draw the shear and bending moment diagram for beam AB and determine the maximum normal stress due to bending. So you can see this is beam AB having point load at C, which is 8 kilonewton, and at E it is 8 kilonewton. A weight of 12 kilonewton is suspended through this pulley, and this is acting downward. As a result, this rope will exert a force upward, which is 12 kilonewton acting on that. And the cross section is shown over here. This is wide flange beam, which is W310 by 23.8. So you have to determine the shear and bending moment diagram. So let's start with the solution. So first step is that if you remove this pin support at point A, so you will be having a vertical reaction force, which is AY, as well as you will have a horizontal reaction force, which is AX. And similarly, if you remove this roller support at point B, so you will replace it with a vertical reaction force, which will be BY. Clear? So we'll find this ax, ay, and by by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0, and force toward right is taken as positive. So ax is acting toward right, and there is no other horizontal force, so it means that ax is equal to 0. Now we'll find this another force, which is you can say ay. So for that we will take sum of all moments about point B is equal to 0, and taking the counterclockwise moment as positive. So you can see this weight which is acting downward will exert a vertical force on this rope, this rope will exert a vertical force on this beam, and let this force is represented by 12 kilonewton. So now we will apply this equation. So sum of all moment about point P is equal to 0. So first moment is due to this force, and perpendicular distance is 1 meter, and this is counterclockwise, so it will be positive. So I can write over here that 8 kilonewton multiplied by 1, that is positive. The second moment is produced due to this 12 kilonewton load, and perpendicular distance is 2 meter, and it is producing clockwise moment, so it will be negative. So I will write minus 12 times 2. The third moment is produced due to this 8 kilonewton load, and perpendicular distance is now 3, and this is also counterclockwise moment, so it will be positive. Plus 8 multiplied by 3, and the last moment that is produced due to this ay, and perpendicular distance is 4, and it is producing clockwise moment, so it will be negative. So minus ay multiplied by 4 is equal to 0. Okay, now we will find this ay. So 4 times ay will be equal to 8 minus 24 plus 36, and we will get here is that this will give us plus 12, 8, 20. Okay, so you can see 8, 3 is 24, not 36. So I will correct it. So this will be 24. So plus 24 minus 24 will cancel. So we will get 4 times ay is equal to 8. And from here you will get 8, ay will be equal to 8 divided by 4, which is equal to 2 kilonewton. Now we'll find the last unknown, which is by, that can be obtained by using the third equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So ay, which is upward, so plus 2 minus 8 plus 12 minus 8 minus 8 plus 12 minus 8 plus by is equal to 0. Okay, so you can see this 8, 8 minus 16 plus 12 is minus 4 plus 2 is minus 2, so by will be equal to 2 kilonewton. Now you have all these reaction forces, so we will able to move to draw the shear force and bending moment diagram. So for that I will take the vertical line from the end of this beam in order to draw the shear force and bending moment diagram. So this is the vertical line. First we will draw the shear force diagram. So for shear force I will take a horizontal line to show length x in meters, and on y-axis we have shear force having unit kilonewton. Let each division is equal to 2 kilonewton. So 2, 4 and 6. Similarly minus 2, minus 4 and minus 6. Okay, starting from point A, you can see at A we have ay, which is 2 kilonewton. So I will draw 2 kilonewton. So this will be your first point. Now moving from A to C, there is no other force, so it will remain horizontal till point C. So I will make it horizontal till point C. Let this is your point C. Okay, now you can see at point C we have minus 8 kilonewton. So 2 minus 8 will give you minus 6. So shear force will change from 2 to minus 6. So I will draw vertical line from this. So this is minus 6. Now moving from C to D, there is no other force, so it will remain same, and we will get a horizontal line till this point. But at this point D, you can see you have a 12 kilonewton load. So minus 6 plus 12 will give you plus 6 at this point. So shear force will change from minus 6 to plus 6. This is plus 6 kilonewton. Now from D to E, again there is no load, so it will remain horizontal. So from this D to this E, it will remain horizontal. And at point E, you have minus 8 kilonewton load. So 6 minus 8 will give you minus 2 kilonewton. So shear force will change from this to minus 2 kilonewton. This is your minus 2 kilonewton. And moving from E to B, there is no other load, so it will remain horizontal. And at the end, you can see you have By, which is plus 2 kilonewton. So it will make this upward to the 0. So from this, you can conclude that you have drawn a correct shear force diagram. Now, we will move toward the bending moment diagram. And for bending moment diagram, you have to draw a horizontal line to show length in meter, x in meter, and on y-axis you have moment, which will be kilonewton into meter. Okay, so what we will take is that we will take this one division is equal to 2. Clear? So 4 kilonewton into meter. Similarly minus 2, minus 4 and this is minus 6. Okay, starting from first point, at first point you have at point A, as x is equal to 0, so moment will be equal to 0. Now the shear bending moment is actually the area under the shear force diagram. So you can see the first area under the shear force diagram is this one, this A1, clear, and this A1 is equal to this height, which is 2, and the length, which is 1. So 2 multiplied by 1, which will give you 2. So first your point will be this 2 at this length. So you will get this point. I will choose blue color. This is your first point. Now you can see that shear force is a horizontal line with 0 degree and bending moment will be 1 degree higher. So it will be a straight line and slope will be increasing because this area is positive. I will draw this vertical line from this, straight line. Now the second area is this area, which is equal to A2, and this A2 you can see this is equal to this height, which is minus 6 multiplied by length is 1. So minus 6 multiplied by 1 will give you minus 6. Okay, so here we have 2 kilonewton. So 2, this 2 minus 6 will give you minus 4. So minus 4 will be at this point, your bending moment will be this one, minus 4. And again you can see you have this shear force is a horizontal line with 0 degree, so and this area is negative, so bending moment will be 1 degree line and the slope will be decreasing, so you will get this straight line. Okay, let me join these 2 points. Okay, now the third area is this A3, and you can see this A3 is 6 multiplied by 1, and this is positive, so A3 is equal to 6 multiplied by 1, which is plus 6. So minus 4 plus 6 will give you plus 2 at this point. So you will get the bending moment at this point will be like this. This is plus 2. And this shear force is a horizontal line with 0 degree and A3 is also positive. So bending moment will be 1 degree line and slope will be increasing. So you will get, you can join these 2 points. So you will get this. Okay, the last one is this A4. So A4 is, again you can see this A4 is equal to minus 2 multiplied by this length, which is 1 meter. So it will be minus 2. So plus 2 minus 2 will give you 0 at this point. So again, the shear force is a horizontal line with 0 degree and this A4 is negative. So bending moment will be 1 degree higher and slope will be decreasing. So by joining these 2 lines, you can complete the bending moment diagram. So what I can write here is that this is BMD, bending moment diagram, and this is shear force diagram. Okay, this was our first part. Now in second part, we have been asked to determine the maximum normal stress due to bending. As we know that maximum normal stress is equal to maximum bending moment mod divided by the section modulus. So you can see here that maximum bending moment, absolute value of maximum bending moment is minus 4 kilonewton into meter mod. That will give you 4 kilonewton into meter. And what about x? Since we have been given that this is W 310 by 223.8 here. So from the table, let me show you. I will go toward the table and we will select the W 310 by 23.8. So you have to go to the property of rolled steel in appendix C. So here you will choose the SI units. Okay, so W310. Okay, now you can see here that this is W310, but 23.8 is here. So what you will get is that you will get this SX, which is 280 into 10 to the power 3 cubic millimeter. So 280 into 10 to the power 3. SX is equal to SX is 280 into 10 to the power 3 cubic millimeter. And if you convert it into meter, so SX will be equal to 280 into 10 to the power 3 multiplied by 10 to the power minus 3 power 3. And this will be cubic meter. So that will give you 280 into 10 to the power 3 into 10 to the power minus 9 cubic meter. And at the end, it will be 280 into 10 to the power minus 6 cubic meter. Now you have both the value, just use this formula. Maximum bending stress is equal to maximum bending moment, which is 4 kilonewtons. So 4 into 10 to the power 3, it will give you Newton divided by SX, which is 280 into 10 to the power minus 6 cubic meter. Okay, cubic meter. And this one is Newton into meter. So it will cancel Newton, 1 meter will cancel with that. So you will get 14.29 into 10 to the power 6 Newton per square meter. That will be the maximum, absolute maximum bending stress. So maximum bending stress in Pascal will be 14.29 into 10 to the power 6 Pascal, because Newton per square meter is Pascal. And if you want to convert this into megapascal, so maximum bending stress is equal to 14.29 megapascal, which is the answer of our second part. And that is all about this problem 5.26. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.